Okay, so this video is on compound interest and depreciation. I'm going to pause every now and again to do some actual calculation. I'll let you know when I'm doing some calculations, so if you want to, you can try doing the calculation to see if you understand what's going on before I do it myself. Okay, so the compound interest formula is just a variation of geometric series. And instead of using instead of using Tn equals AR to the n minus 1, we use the compound interest formula, which is closely related, but it works by saying A equals P outside of 1, and for compound interest we go plus R to the n, and for depreciation or compound shrinking, we would use A equals P outside of 1 minus R to the n. Look, sometimes you'll see these written with slightly different numbers or letters here, slightly different letters. As long as we understand that this is the initial amount, our starting amount, and that this is growing by a rate, and this is shrinking by a rate. Let's apply it here. Ruby invests $16,000 in the bank at an interest rate of 2.6% per annum. How much is the investment worth after 5 years? So there are 3 important bits of information. We want to know how much the investment is worth. We're trying to find this side here. We know the principal or starting amount is $16,000. And we know it's 1 plus, now you can write 2.6% if you want, your calculator will accept 2.6%. Hope you don't mind, but I like to write 0.026 to mean 2.6%. And then the time periods, 5 years, 5 up here. Now that would go straight into your calculator. If you'd like to use my fumbling time as time to try and check your own answer, you might want to pause and try that yourself. So 16000 outside of 1.026 all to the power of 5. Right, so the answer I got was the amount after 3 years is 18,191.008, so we generally round to the nearest whole cent when we're dealing with monies. Right, a variation on this. Exactly the same initial number, but I just want to point out this important variation. It's still 2.6% per annum, but this is compounded monthly. It's still for 5 years, but because it's compounded monthly, we have to change what we do slightly. It's still A equals P outside of 1 plus R to the n, but these two amounts here have to reflect compounded monthly. How? How are they going to reflect that? Okay, so we still start the same way. A equals P outside of 1 plus, but the rate has changed. This is 2.6% per annum, which means 2.6% if it was calculated each year. Per annum, each year. But we want to compound monthly. So we need to take this 2.6% or this 0.026, I don't care how you write it, we need to share it evenly over 12 months. So now we've got 12 payment periods in each year. And we want to know how many payment periods do we have altogether, or calculation compounding periods. If there's 5 years and we're compounding monthly, then we must have 5 lots of 12 months. So there are 60 payment periods. So now that we've plugged our values into our formula, we literally just grab our calculator and we play. So feel free to pause and see if you can get the same answer as myself. Meanwhile, 0.026 on 12. I'm just editing what I put into the calculator rather than retyping it all out. So now it looks very similar, but that's because our interest rates And look, this is a fairly realistic interest rate for investments at the moment in banks, 2.6%. That's because at the moment our interest rates are quite low, but they do fluctuate, and in your lifetime you may see them do all kinds of wacky things that I've never seen before. 18218.69 is how many dollars they get out. So a little interesting point is that there is a difference, and that difference is just about how often you compound or make the calculation of the change. Okay, let's have a quick look then at, sorry about that, jumped away fairly quickly. Let's have a quick look at depreciation. Now depreciation, sometimes instead of writing A equals P outside of 1 minus R to the N, you might see this written as SO equals P 1 minus R to the N. Same formula. It's just that some people write SO to mean the salvage value of something. And often this calculation, this depreciation calculation, is used to try and pay less tax. And so this is a common formula used in taxation. Anywho, let's have a look at this. It was initially brought for, so we want to know what's it worth at the end. A equals, and I'm just going to use this formula here, P being how much it was bought for, 23,000, outside of 1 minus 0.18 to the power of 4. Alright, and this time I'll pause again. You can see if you can get the same answer as myself. 23,000 outside of 1 minus 0.18 to the power of 4. So this will have shrunk in this very short amount of time to $10,398.80. Dollar. Squeeze a dollar in there. It's not very neat, but hopefully you get the idea. Okay, sometimes people like to work this part out before they do the calculation, and that can help to have an idea of what's actually happening. 1 minus 0.18 is 0.82. What does that really mean? I mean, this is not fundamental. If you understand what's happened up to here, we're good. I'm just getting this point across that this is eventually, after it's raised to a power, is going to be multiplied by this. This thing here is going to make a whole number shrink. Because it's less than 1, it's between 0 and 1, whenever you multiply a decimal or a fraction by a whole number, it makes that whole number shrink when that decimal is between 0 and 1. So that's how that depreciation is occurring. Some people like to work that out and put this value in instead of 1 minus that. Okay, look, here's an application. Oh dear, I've done it again. Here's an application question. So this is, an iceberg is melting in the ocean, shrinking at a rate of 12.5% per day. So what is it? Are we doing compound interest or growth, or are we doing depreciation, decay? It's melting, it's shrinking, it's melting, shrinking, so it must be decay. So I want the amount is equal to what I started with, 1 minus the rate to the power of n. It has an initial volume of 30,000 meters in 3 dimensions, or 30,000 meters cubed. In which day will it fall below 5,000 meters cubed? So what do we have so far? We've got the rate of 0.12. We've got the initial volume, which is P. What we don't have is the n value. We don't know what the heck that is. But we are given this 5,000. That's actually the amount that we would usually find just by plugging and playing. So this time we can't plug and play. We have to rearrange. So let's put in what we know. We know that the amount we're after is 5,000. We know that we start with 30,000. And we know the rate will be 1 minus 0.12. And we know that there's an n up there. I'm just going to tidy this a tiny bit. I like to write this out as just one number. It makes it a little easier to see. 1 minus 0.12 is 0.88. Now, I need to somehow get that n by itself. This and this thing here are tied together by a multiply. So I can divide both sides by 3,000 to shift that over here. So I'll get 5,000 on 3,000 equals 0.88 to the power of n. Now at this point, there are two ways of doing this. Some people really like to use guess and check method. They work this out as a number, which is 5 on 3, which is 3 goes into 5 once, remember 2, so 1.6 recurring. No, 1.6 recurring, sorry about that. Equals 0.88n. And some people will just write 0.88 and guess and check values of n until they get this number or something close to it. If that is your preferred method, you can use that method. I have also been exploring the log method. And for those of you that haven't seen it before, bear with it, because I think it will actually, you'll find it is quite achievable. What we're going to do is take the log of both sides. Now it really is just as easy as writing it. 5,000 on 3,000. I'm not explaining that, I'm just saying that's what we're doing. We're doing a thing called taking the log. And just like you would multiply by both sides, or divide by both sides, or add by both sides, taking the log is something we can do to both sides. And what taking the log allows us to do, it allows us to do one thing, and that is shift that down to here as a multiply. That's all it's used for. So then I have log 5,000 on 3,000 equals n log 0.88. Now we don't have to know what this means. It's just a number, and our calculator knows what that number is. What's in between the n and this number is a times. So if I divide both sides by this thing here, I get n by itself. So let's divide both sides. It becomes log 5,000 on 3,000 divided by log, it's just a number, divided by a number. Your calculator knows what those numbers are. We don't have to worry about it. Equals n. And we literally find the log button on our calculator and type exactly this in. We can type exactly this into our calculator. If you would like to pause while I try and work that out and type it in, and you can try finding the log button on your calculator if you haven't done this already, and see just how easy it can be to just type in a fraction with log on top, log underneath, and see what you get out. Okay. Oh, sorry, I dropped a 0 off. That should be 30,000, not 3,000. My mistake. I'm just going back and putting that 0 in. I'm not going to redo the whole video. We're just putting a 0 in. How did I know that I made a mistake? I should not get a negative number. All I'm doing is going back in and putting a 0 to make that 30,000 and not 3,000. So, and there we go. We get n equals 14.016. Sorry about that. Hopefully you saw when I dropped off the 0. 14.016 equals n. So in the 15th day, because 14 days have passed, in the 15th day it will fall below whatever the heck, 5,000 cubic meters. Okay, well, that's an overview of compound interest and depreciation. I hope that was useful. Sorry about the mistake at the end. And if you have any questions between now and Thursday, feel free to email me. And good luck studying. Thanks, girls.